Dr. J. Durga Devi, working as Assistant Professor in the Department of Electronics and Communication Engineering at College of Engineering Guindy, Anna University. Her area of research includes analog and digital circuit design. Her PhD work was CMOS realization of clock generator circuits for microprocessors. She teach electronic circuits, signals and systems, digital VLSI and data converters. She has 16 years of teaching experience.
Welcome to UGC lecture series on practical session. So, now let us see the design of high pass filter, first order high pass filter using op amp. So, this active first order filter, high pass filter uses an ideal op amp, and that is we will see the design based on an ideal op amp. The characteristic of ideal op amp is presented here. So, this ideal op amp has an infinite gain. So, that is for a finite V out, input voltage is 0. So, that is the input voltage here is VID. So, this VID is 0. Now, the second characteristic is it has infinite input resistance. So, therefore, the current drawn into its input terminal is 0. It has 0 output resistance. So, therefore, it acts as a perfect voltage source, and it has 0 V out for 0 V in, that is there is no residual output voltage, and it has an infinite bandwidth, that is it amplifies all the signal for all the bandwidth, that is for the entire frequency range, it can amplify the signal, input signal. So, we will see the frequency response characteristic of the first order filter, and this characteristic we will see for a Butterworth characteristic. So, first let us see for an ideal filter. So, ideal filter, a high pass filter we will see. So, the frequency response characteristic for an high pass is for a frequency less than FL, the gain of the filter here is 0, and frequency greater than FL, the gain here is given by AF. So, the frequency here is the characteristic here is the frequency of input signal is swept and the gain is plotted. So, the gain here is given by V out by V in, output voltage by input voltage. So, for frequencies less than FL, that is for input frequencies less than a specific frequency FL, this gain that we get is 0. So, AF here is V out by V in. So, the frequency of this V in is varied, and gain that we get from the filter is plotted here. So, for frequencies greater than FL, what we get is this V out is AF multiplied by V in. So, this V in being kept constant, this amplitude of the signal being kept constant. So, what we get is the gain here is being given by V out by V in, and with this being constant, what we get is this will be constant here. So, for frequencies greater than FL, this band is termed to be pass band, where we have constant gain. So, this is a characteristic of the first order filter, and it is an ideal filter, and it is termed to be brick wall filter, and this characteristic is closely approximated by this Butterworth characteristic. Since this filter is not practically realizable, it is closely approximated by the Butterworth characteristic. So, this Butterworth characteristic has a maximally flat pass band, and since it is a first order, attenuation at the frequency FL is minus 3 dB. So, this FL frequency is termed to be cutoff frequency or 3 dB frequency, and for frequency less than FL, the roll off rate here is minus 20 dB per decade. So, this is a characteristic of Butterworth, and so this high pass filter characteristic we will see how it can be realized by circuit. So, the filter realization is this. So, there is the first order section, a passive filter section. Output of this passive filter section is taken to an op amp section. So, this op amp here is connected in non inverting configuration. So, this passive filter section, if you see here, it is to the input signal, there is a capacitance which is connected in series, and after that what we have is a resistance here. So, this is R. So, R that we have here, and this is C here. So, in terms of impedance, if you write this capacitance, so this is Z, impedance of this capacitance is 1 by j omega c, and it is a function of frequency. So, for very low frequency, what we see is for frequency very closer to 0, we will assume that it is 0 now. So, that is the DC signal. So, for omega tending to 0, what we have is this Z will tend to infinity. So, with Z tending to infinity, so this capacitance will act as open. So, the C will act as open. So, for omega tending to 0, so omega is frequency in radians per second. So, this frequency tending to 0, what we see is this capacitance here act as open, and therefore, the signal input voltage is not connected to V 1. So, this node voltage V 1 will not have any effect on V in. So, this end is looking like an open here as an open circuit. Now, as this frequency is increased, so now as we increase this omega, so this impedance here decreases. So, the impedance decreases as we increase omega. So, therefore, the resistance contributed by this capacitance will become smaller and smaller from the initial condition of infinite, and the voltage will now appear across R. So, that will be a potential division of V in, that will be across R. So, if you consider a finite impedance of Z in, so what we will see is voltage across R will depend on V in now. So, this voltage will be amplified by the op amp here. So, now we will express V 1 for all frequencies in terms of V in. So, this if we express V 1 in terms of V in, so what we have is a capacitance here which is 1 by j omega c. So, this capacitance impedance is expressed as a function of frequency, and then what we have is a resistance R. So, this side is V 1 for us, and what we have here is V in. So, the current here is through this way, because the current into this is the op amp terminal. So, this current is 0. So, current in is 0. So, the entire current will be through this loop. So, therefore, voltage across R here. So, that is V 1 here. So, this V 1 is expressed as V in into R divided by R plus 1 by j omega c. So, therefore, this can be written as V in R j omega c divided by R j omega c plus 1. So, that is the expression which is shown here. Omega here is in radians per second, which we can express as 2 pi f, f is in hertz. So, what we have is V 1 here is now. So, that is this terminal potential V 1 here is j into 2 pi f R c V in divided by 1 plus j 2 pi f R c. So, this V 1 is amplified by the amplifier, and finally, what we get is V out. So, V 1 is what we have seen in the previous slide. Now, so this configuration what we have here is V 1 is this terminal, and so current drawn by the op amp is 0, and the gain of this amplifier is infinite. So, for a finite V naught, this input voltage is 0. So, input voltage here is V 2 minus V 1. So, that is the input voltage. So, V 2 minus V 1 will be 0. So, it is V 2 is equal to V 1. So, the current drawn is 0 here. So, therefore, this side will act as an open circuit. So, that is what is shown here. So, this side of the circuit will act as open circuit. What we have is V 2, and then it is R 1 RF that is connected to V naught here. And since this op amp has an infinite gain, this V 2 will be equal to V 1, because V I D will be 0. So, therefore, V 2 is written as j into 2 pi f into R c V in divided by 1 plus j 2 pi f R c. So, V 2 is equal to V 1 here. So, that is the expression we have used, and V naught here is this is gain of the non-inverting configuration multiplied by V 2. V 1 V 2 is equal to V 1. So, it is gain of the non-inverting amplifier multiplied by V 2. So, V naught can be expressed as 1 plus R f by R 1 multiplied by V 2 here. So, with this if you express V naught by V in, so this is the form we have, which is 1 plus R f by R 1 j into 2 pi f R c divided by 1 plus j 2 pi f R c. So, this is the gain of this filter active high pass filter as a function of frequency. So, this is a transfer function of the filter. So, this from the previous section, the expression that we have got is this. So, in this let us take this as constant as FL is 1 by 2 pi RC, and then we will use this as AF. So, V naught by V in now can be expressed as AF, J, F. This entire term here is 2 pi RC is 1 by FL. So, what you have is J, F by FL divided by 1 plus J. So, this is F and the left out term is 2 pi RC. So, in place of 2 pi RC you can substitute as 1 by FL. So, it is AF J F by FL divided by 1 plus J F by FL. So, this is gain as a function of frequency. So, now the expression for gain, it is a complex polynomial. So, therefore, if we have to find out its magnitude, then it is V naught by V in, which is given by AF F by FL divided by square root of 1 plus F by FL the whole squared. So, what you can see from here is, so this being complex, so this will have magnitude part and the phasor part. So, we will find out what is its magnitude part. So, the magnitude part is this. If you take magnitude here, it is AF, in the numerator it is F by FL, and then the denominator what we have is there is a real, and then what we have is an imaginary term. So, it is square root of 1 plus F by FL the whole squared. Now, we will see the characteristic of high pass now. So, now for frequencies much smaller than FL. So, for much smaller than FL, so in high pass it is the stop band. For much smaller than FL, so this term is if F is much smaller than FL, so this term is smaller than 1. So, what you can approximate is this denominator is 1. So, V naught by V in mod of that is AF F by FL. So, this gain is now linearly related to F. So, as frequency increases, so this gain will increase. If F is 0, what you get is gain is 0. Now, at F is equal to FL. So, at F is equal to FL, what we have is this is equal to, so if you substitute here at F is equal to FL, so this is 1 here, and here what you get is 1 plus 1, so it is square root of 2. So, it is AF by root 2. So, at F is equal to FL, what you get is AF by root 2. So, in decibels if you express this, it is AF minus 3 dB, and this frequency is termed to be 3 dB frequency. And for F much greater than FL, so when you consider F much greater than FL, this term will be much greater than 1. So, what you get is in the denominator you will have F by FL, and numerator we have F by FL. So, therefore, this gain here becomes AF. So, for frequencies much greater than FL, this gain is constant and it is given by AF. 3 dB we have AF by 3 dB frequency, and it is termed to be cutoff frequency, we have AF by root 2, and for frequencies much smaller than FL. So, this is the characteristic which is linearly related to F. So, as frequency decreases, so this gain will also decrease, and F becomes 0. So, this gain becomes 0. So, this is a characteristic of the Butterworth high pass filter. So, this is a characteristic we get. So, for F greater than FL, it is constant, and at F is equal to FL, it is 3 dB, and then what we have is it is the gain here is linearly related to F for F smaller than FL. So, the rate here is roll off rate is minus 20 dB per decade. In decibels if you express, it is minus 20 dB per decade. So, we have seen magnitude response in the previous characteristic. So, this is a general expression for the gain, and we will see its phase response now. The transfer function V naught of S by V in of S is given by this. S is J 2 pi f. So, 1 plus R f by R 1 J 2 pi f R c divided by 1 plus J 2 pi f R c. So, this is expressed as V naught by V in, and this we have seen in the previous slide. F L is 1 by 2 pi R c, A f is given by this, and V naught by V in is this, which we have seen in the previous slide. Now, the phase if you express here, in the numerator what we have is a 90 degree, and in the denominator with 1 plus J f by F L, what we have is this is A plus, if you consider this as real part A plus J B, an imaginary part. what we have in the denominator is minus tan inverse of f by fl. So, this is the phase that we get, and this phase is a function of frequency. This frequency is the input signal frequency. Now, the three cases if you consider, that is f much smaller than fl, which is the stop band, and we will consider the case with f is equal to fl, this is at 3 dB, and f greater than, much greater than f, which is this pass band for the high pass filter. For the first case, for f much smaller than fl, so f much smaller than fl is this theta is very small here. So, if you consider that, this if you can express phi minus 90 degree, which is minus tan inverse of f by fl, and if you take tan on the other side, so it is what we have is tan inverse of f by fl 90 degree minus phi is what we will have, and if you take this f by fl as very small, so tan of phi will be phi. So, therefore, with that what we get is phi is equal to 90 degree minus f by fl. So, tan phi is phi, and what we get is phi is equal to 90 degree minus f by fl. So, f is 0, with f being 0, what we have is a 90 degree phase shift. Output signal will be 90 degree phase shifted in comparison with input signal, and if you consider f is equal to fl, so that is at f is equal to fl, what we have is tan inverse of 1. So, that will be 45 degree here. So, 90 degree minus 45, what we have is phi will be equal to 45 degree. So, this is at f is equal to fl. So, this case you can see here, with if you operate at a frequency, the input signal if you operate at a frequency which is equal to fl, so that is at the cutoff frequency, output voltage is ahead of the input voltage by a phase shift of 45 degree. What you can see is output signal is earlier than input signal by a phase offset of 45 degree. Now, with the case of f greater than f, that is when f is considered to be much greater than fl here. So, this case here is what you get here is as f tends to infinity. So, here it is 90 degree. So, phi here is 0 degree. So, for much greater than fl, so that is in the pass band. So, this phase is 0. So, if the phase is 0, output voltage will be aligned with input voltage. So, the inference from here is the response, the frequency response of this amplifier, there will be a phase shift. So, the phase shift, the maximum phase shift can be 90 degree. So, the filter introduces phase shift in the input signal, and the maximum phase shift introduced can be 90 degree. Now, with this the magnitude is of great importance since it is a filter. So, we will use magnitude response and we will design the filter. So, let us see the design procedure, and we will see an example to design the circuit. So, the design procedure here is, first we will choose the cutoff frequency, the frequency up to which the signal has to be attenuated, and after which it has to be passed. We will choose this depending on the application, and then with FL chosen, and FL is given by 1 by 2 pi RC, we will choose C to be a practically realizable value, and from this expression we can obtain a value of R. So, this R and C, once we know, this passive filter section is decided, and the next section is this op amp section, which has these component values R1 and RF. The gain from the op amp is 1 plus RF by R1. So, depending on the gain required in the pass band, we can choose this ratio of RF to R1 depending on the gain required. Component values can be chosen based on that. So, we will see a numerical example for that. So, the example here is design a high pass filter with a cutoff frequency of 1 kilohertz, and pass band gain is 2. The requirement of gain is 2, cutoff frequency is 1 kilohertz. So, FL is 1 kilohertz. So, we will choose this capacitance as 0.01 microfarad, and we will calculate R from the cutoff frequency expression, which is 1 by 2 pi. F here is 1 kilohertz, and then what we have is the capacitance here, which is 10 power minus 8, and then with that the resistance that we get is 15.9 kilo ohm. So, R here must be 15.9 kilo ohm, C that must be used here is 0.01 microfarad, and the gain, pass band gain, what we want is 2. So, we will choose R1 RF to be equal to 10 kilo ohm, because what we know AF is 1 plus RF by R1. So, RF by R1 must be equal to 1. So, we will choose this RF and R1 to be of the same value, and we have chosen it to be 10 kilo ohm here. So, you can substitute these component values here, and experimentally you can verify the frequency response of this filter. To verify frequency response of this filter, this input signal frequency must be varied, say from DC to if cutoff frequency is 1 kilohertz, you can go up to 2 decades from there. So, up to 100 kilohertz, this input signal frequency can be varied, and then with input voltage fixed, that is kept constant, V naught must be noted. So, V naught by V in has to be calculated for various frequency settings of V in. With that, a frequency response characteristic of the filter can be plotted. So, the design that is carried out is with a cutoff frequency of 1 kilohertz. So, since it is a first order, the roll off rate here is minus 20 dB per decade, and it is designed with a passband gain of 2. So, since it is a high pass, the input signal will be fed to input will be fed to the capacitance, and the resistance will be connected to a ground which is from a series RC circuit. So, the components required here will be, we need a supply source, a power supply source, and a signal generator, and an oscilloscope to observe the signals. The passive circuits will require R and C, and the op amp circuit, which is used for providing gain in the pass band, is constructed with IC 741. So, IC 741 will require plus 12 volts for VCC and minus 12 volts for VSS. So, now connecting the input signal and supply sources, we will observe signal at various points, we will verify passband gain, and then we will verify cutoff frequency. After that, we will see whether the desired roll off rate is met or not. So, the supply voltage is derived from a DC supply source. So, plus 12 volts is derived between the plus terminal and the common terminal, which is a ground terminal, and this plus 12 volts is connected to the 7th pin, and the negative voltage, which is minus 12 volts, is derived between minus terminal and the ground, and this negative voltage is connected to the negative supply source of negative supply pin of IC 741, which is the 4th pin. So, the input signal to the filter is derived from the signal generator that is there in this mixed signal oscilloscope. So, the signal generator signal is derived from this port, and the signal is set for an amplitude of 1 volt peak to peak, and the signal frequency is set to 100 hertz. So, we can adjust this and set the desired frequency and the desired amplitude. The output signal is observed from the oscilloscope. So, output signal from the filter is connected to one of the channel. So, the oscilloscope has 4 channels here. So, it is connected to the first channel, and the output signal amplitude and frequency can be observed in the display. So, with the cursors set here, you can observe the peak to peak amplitude here. So, the peak to peak amplitude here is now is 351 millivolt. The Y1 cursor here, so this Y1 cursor here is set at the highest amplitude, and the Y2 cursor here is set at the lowest amplitude. With this, the difference in the amplitude will give the peak to peak voltage, which is 351 millivolt. So, similarly, we can measure the frequency of the signal by using the X cursors. The signal frequency can be measured using the X cursors here. So, the X cursor here, one is set to the peak point here, and the other is set to the next peak point here, which will determine one period for the signal. So, when it is set, you can find out from the measure here, which is about 10 milliseconds. So, if it is 10 milliseconds, then this corresponds to 100 hertz. Plus 12 volts is connected to 7th pin of IC 741 amplifier, and the negative potential, which is minus 12 volts, is connected to 4th pin of IC 741. So, the pin configuration here is can be is numbered with the notch here. So, the first pin is from here and then it goes on and it is up to this end is the 8th pin. So, the 7th pin here is with the plus supply and the 4th pin here is with the negative supply. Now, the circuit configuration here, one section here is this the passive filter section, and then what you can see is the resistor here, the two resistors here. So, this will RF and R1. So, this resistor here is the RF resistance, the feedback resistance, which is connected between the negative terminal and the output pin here. So, the negative terminal here is the second pin here and the output pin here is a 6th pin for the 741, and the other resistance which is R1 here, which is connected from the negative terminal, which is the second pin. So, the passive RCs which constitute the low pass filter, the input signal here is now connected to the capacitance one terminal, the other terminal here is connected to the third pin, which is a positive pin. Now, from the positive pin what we have is the resistance here. So, there are two resistances in series that is connected to ground here. The filter is now configured for 1 kilohertz cutoff frequency. So, therefore, these two resistances, they are with a value of 15.9 kilo ohm and this capacitance is of value 10 nanofarad, and the resistances here which is RF and R1. So, these are chosen for a gain of 2. So, this is with 10 kilo ohm and this resistance is with 10 kilo ohm. So, with RF and R1 as 10 k, what we get is a gain of 2 from the op amp amplifier, which is configured as non-inverting configuration. Input signal set as 1 volt and the frequency can be varied and the gain in the pass band can be verified. Now, the frequency here is it is 10 kilohertz now. The frequency that you can see here is 10 kilohertz. So, 1 kilohertz is a cutoff frequency. So, 10 kilohertz is in the pass band and the amplitude peak to peak voltage that you can see in the oscilloscope is 2 volts. So, in the pass band the input, since the input signal is 1 volt and the output voltage here is now 2 volts, the gain is now 2. So, which is the desired one. Now, as the frequency is varied and when it is brought closer to 1 kilohertz, you can see this amplitude getting attenuated. So, we will see as the frequency is varied. So, now the frequency is reduced. So, the amplitude remains constant, that is the peak to peak voltage remains constant, which is the same as 2 volts. So, that is within the pass band, and as the frequency is reduced and when it is brought closer to the cutoff. So, now it is at 1 kilohertz, we will verify the peak to peak amplitude. So, this peak to peak amplitude must be 1 by root 2 of the maximum voltage. So, that is in decibels it is 3 dB and it is termed to be the cutoff frequency. So, let us verify the peak to peak amplitude. So, we will adjust y to cursor now. And the peak to peak amplitude now that is read is about 1.475 volts. Now, at the cutoff frequency what you can observe here is it is about 1.475 volts. The expected one is 1.414. So, this is because of the tolerance that we have in the capacitance. So, what we have used is 10 nanofarad. So, with the expected tolerance this can deviate. So, it is closer to 1.414 and this is the cutoff frequency that you can see is it is 1 kilohertz. Now, as the frequency is varied, the signal amplitude gets attenuated. So, it becomes lower and lower. So, this is its stop band. Now, to measure its amplitude, so we will adjust its time division, so that it is observable within the screen here. So, we can see its amplitude getting reduced. Now, 1 decade away from the cutoff frequency. So, this is at 100 hertz now, the input signal frequency is set to 100 hertz. Output signal with the output signal observed. The peak to peak amplitude is now 288 millivolts. The corresponding decibels is minus 10.8 dB. Now, if you compare from the cutoff frequency, it is about 14 dB down. Since it's the reading that is taken now is closer to cutoff frequency. So, there is a deviation from the expected. The expected is about 20 dB per decade roll off. Now, the reading is taken closer to cutoff. So, that is why there is a variation here. Now, we have verified the passband gain, which is 2 in this is after 1 kilohertz, and the cutoff frequency we have verified as 1 kilohertz, and the roll off rate is now closer to 20 dB per decade. So, this shows the operation of a high pass filter, and it is a first order filter. To test your understanding, try to answer the following question. So, the first question is, so design the high pass filter now with a cutoff frequency of 10 kilohertz. So, this is choose this cutoff frequency as 10 kilohertz and use this passband gain as 5. So, this is question 1, and question 2 is, so the configuration that we have used is non-inverting configuration. Now, use the same op amp in inverting configuration and obtain a passband gain of minus 5. So, gain is minus 5, and cutoff frequency here again use this as 10 kilohertz. So, try to design the two specifications given. Thank you.